Hi, I'm Vinay and I'm back with some exciting news. I have added electromagnetism lectures, beautiful short methods in electromagnetism to the Game Changer 2022 course. If you're new here, go to vinayopal.com right now, select on courses. If I go to the Game Changer 2022 course, just click on more details. You'll find all the course lectures here. You can click on start a free trial and watch the free lectures available to see what this course is all about. For the hundreds of those of you who have already bought my course, I have added electromagnetism lectures, and there are 5 lectures here. The fifth one is under construction, is going to come soon. The rest of the four lectures are what you can watch. So these are some lectures on short methods ranging from chapters like electrostatics all the way up to RL circuits. And in today's video, I'm going to give you a very short preview, just some short sections of a couple of lectures from the electromagnetism chapter. So you'll get an idea of what I have included in these videos. Here you go. Enjoy. Now, if I have this kind of a situation where these two branches are in parallel, so this is very similar to cells in parallel. It's just that the capacitances have now been replaced by resistances. So I want to follow the same process that I did, and I want to replace the system by a single battery of equivalent and a single capacitance C equivalent. Alright, so let's say that the change in potential across the each branch is delta V should be the same change in potential across the equivalent cell equivalent branch as well. So I can have E1 minus Q1 by C1 should be equal to delta V. So that means Q1 would be equal to C1 times E1 minus delta V. Similarly, I can write Q2 as C2 times E2 minus delta V. And for the equivalent situation, I can write the total charge that is flowing, that has gone to the equivalent capacitance, is the same charge that has gone to the entire system of the two branches. So which I have labeled as Q. So I should be able to write Q as C equivalent into E equivalent minus delta V. And therefore now I have Q is equal to Q1 plus Q2. The charge that is coming here is getting split in Q1 and Q2. And so I'll have C equivalent E equivalent minus C equivalent delta V should be equal to C1 E1 plus C2 E2 minus C1 plus C2 times delta V. Now this is very similar to what we did in the resistance case. Once again, I'm going to compare the coefficient of delta V. Delta V is the variable here. We should be able to replace this system of two branches by the equivalent battery and equivalent capacitance for any delta V. So the coefficient of delta V should be equal. So basically, I will have that C equivalent should be equal to C1 plus C2 as expected, because these capacitors, because these branches are in parallel. So I'll have C equivalent is equal to C1 plus C2. In the resistance case, remember we had gotten 1 by R1 is equal to 1 by R1 plus 1 by R2 was equal to 1 by R equivalent. And I will also equate the constant terms here, and therefore I will have E equivalent is equal to C1 E1 plus C2 E2 divided by C equivalent, which is C1 plus C2. So it's a pretty straightforward formula, but it will be very useful to remember this. If you remember the resistance formula, in the resistance case, I had equivalent was E1 by R1 plus E2 by R2 divided by 1 by R1 plus 1 by R2. So in the capacitance formula, it's just that 1 by resistance has been replaced by capacitance. You can remember it that way. So instead of 1 by R1, you have C1. So you'll have C1 E1, 1 by R2, you have C2. C2 E2 divided by 1 by R1 plus 1 by R2 is basically C1 plus C2. So here I have laid the foundation for the circuit analysis that we are going to do and the problems that we are going to solve in the coming pages. Now let's look at a capacitor question. So let's say I have 3 branches. And the EMF is, let's say, E, 2E and 4E, and the capacitors are C, 2C and 4C. The question is asking us find VA minus VB. So I want to find the potential difference across points A and B. So here I can combine all these capacitor branches using our capacitor formula. If you remember this expression for capacitors, when you have these branches in parallel, the formula was C1 E1 plus C2 E2 divided by C1 plus C2, and C equivalent of course was just the parallel addition. I'm going to use this expression. So I'm going to write this entire combination as a single battery and a single capacitance. So E equivalent, C equivalent between points A and B. So my E equivalent will come out to be, the formula was C1 E1 4CE for the top branch plus C2 E2. So again 4CE plus C3 E3 again 4CE divided by C1 plus C2 plus C3. So 4C plus 2C plus C. So this will be 12E divided by 7. So this is my E equivalent from A to B, across A to B. So here you have to realize that this is a closed circuit. What I mean by that is there is no charge flowing in from A and then out from B or anything of that sort. And therefore the total charge that has gone from A to B is 0. The total charge, once again I am repeating, that has gone from A to B is 0. That is also basically the junction rule at B or at A. So there is no charge that has flown across the C equivalent. The charge here is 0. There is no charge going from A to B. So the only potential difference across AB is due to the battery itself. So I can basically write that VB minus VA should be equal to E equivalent, which is 12E by 7. And therefore my answer, I have asked you VA minus VB. So VA minus VB would be minus 12E by 7. So I hope you've understood how we solve this question very quickly without resorting to Kirchhoff's laws. Suppose you are asked the charge on any capacitor. In more than one correct questions, they can ask you to find the charge on any one of these capacitors. So let's say I want to find the charge on this 4C capacitor. So what I'm going to do is, that I know the potential difference from A to B is 12E by 7. So across the uppermost branch, I just go from A to B and I write the change in potential VA plus E, and let's say the charge here is Q. So potential will drop by Q by C, so Q minus Q by 4C should be equal to VB, and I already know what is VB minus VA. So I have E minus Q by 4C is equal to VB minus VA is 12E by 7, and thus you will get your charge on the 4C capacitor as minus 20 CE by 7. Now this negative sign just denotes that what I assumed was that the left plate of the 4C capacitance is positive Q. So that positive Q is coming out to be minus 20 CE by 7. So we'll report the answer. If they ask you the charge on the 4C capacitor, your charge would be, you report the positive value. So if they just ask you the charge on the capacitor, that will be 20 CE by 7. And specifically the left plate will be negatively charged, the right plate will be positively charged according to the sign that we have gotten here. So I hope you understood how we can calculate the charge on any capacitor as well. Now let's come to RC circuits. Here the powerful nature of this short method really comes into play. So first let me just discuss the standard RC circuit. You have a capacitance, a battery and a resistance, and let's say current I is flowing, the charge on the left plate is Q, charge on the right plate is minus Q at some instant. So my loop law will be, as I go, let's say I go in the clockwise manner, I go across the EMF E, then I go from Q to minus Q, potential will drop, so minus Q by C, and then I go across the resistance, minus IR is 0, and using the fact that I is equal to dQ by dt, you should be able to solve this equation and get the charge as the standard equation. Here we've assumed that the charge is 0 at t equal to 0. So if nothing has been said in the question, you can always assume that that the capacitor plates are uncharged initially, and of course you differentiate this and you will get the current as well. So here RC is what we call as a time constant. So these are very standard things that you would have learnt in a study of current electricity. So this equation for the charge at least is what you should definitely remember for your exam. You can always get the current by quickly differentiating the charge, but the charge expression is something that you should definitely remember to save some time. Now we are going to look at what happens when you have more than two branches in your circuit. So suppose you have multiple batteries or multiple resistances or even multiple capacitors. How do you find the charge as a function of time, or current as a function of time, or even the time constant? So these are the type of questions that can be asked. So let's take a look at that on the next page. So let's say I have a battery of EMF E, capacitance C. I have another battery of EMF E, let's say capacitance is, let me just take general cases, C1, C2, and let's say I have another capacitance C3 and the resistance R here. Now I want to find the charge as a function of time on the capacitance C3. Alright, so in such questions, let me first show you the standard method. So for the standard method, I am going to assume I have current, let's say I1, I2, and let me say this is I3. And let's say the charge on capacitor C1 is at some instant is Q1, on C2 is Q2, and on C3 is Q3. So one equation is of course that I1 plus I2 would be equal to I3. This is just the junction rule. Now I'm going to write loop law. So let me write loop law, let's say in the uppermost loop first. So let me just redraw that diagram. E1, C1, sorry, my mistake, E C1, E C2, and of course you have the lower branch as well, but I'm not drawing that for now. I'm going to write the loop law here. Right, so I have a current I1 flowing this way, I have a current I2 flowing this way. So as I go across the upper battery, I'll have EMF E, and then I have charge Q1 here, so potential will drop Q1 by C1. This is Q2 minus Q2. Now I'm going from minus Q2 to plus Q2 across C2, so the potential will increase. And then I go from the higher potential to the lower potential of the lower battery, so that will be minus E should be 0. So I have just written the loop law here. So I get one equation as Q1 by C1 is equal to Q2 by C2. If I differentiate this, current I1 is dQ1 by dt, so I can also write I1 by C1 is I2 by C2. I've just differentiated the charge relation on both sides. Alright, so I have this equation. Now, I can also write, I'll need to write another loop law. I have to involve I3 as well. So let me just write the loop law along the outermost boundary this way. So let me just draw that circuit here. Of course, you have the middle branch as well. I'm just not drawing that for a little bit of clarity. So I'm going to write my loop law across the outermost loop. So this is E, C1, C3 and R. I have current I1 flowing this way. I have current I3 in the lowermost branch. Remember, there is some middle branch as well of E and C2, but I've just not drawn that. Alright, so I'll go across E. So I'll have my equation will be E. Then I'll go across capacitance C1. This charge is Q1, so potential will drop. Then I go across the resistance minus IR, I3R. And then I'm going from Q3 to minus Q3. So the potential will drop across C3 as minus Q3 by C3. This should be 0. Now what I'll have to do is I'll have to express everything in terms of Q3 or I3. So see, I have one relation that Q1 plus Q2 would be equal to Q3. It's just an integral version of I1 plus I2 is equal to I3. And I also know Q1 by C1 is Q2 by C2. So let me just write Q1. I'm going to substitute Q2 as Q1 C2 by C1 is equal to Q3. So basically Q1 comes out to be C1 divided by C1 plus C2 times Q3. And I'm going to substitute this Q1 here. So that will be my next step. You can already see the standard method is getting really long. Which is why, of course, I'm going to show you the short method as well. But let's just finish this standard method on the next page. Just remember this equation that I've written here. I'll just write that down on the next page as well, and then I'm going to substitute Q1 as this value. So my equation was E minus Q1 by C1 minus I3R minus Q3 by C3 was 0. This was my loop law. And I had gotten Q1 is equal to C1 divided by C1 plus C2 times Q3. So let's just substitute that here. So I'll have E minus Q3 times 1 by C1 plus 1 by C2 minus Q3 by C3 minus I3R is 0. And therefore I'll have E minus Q3 divided by 1 by C1 plus 1 by C2 plus 1 by C3. Let me just label this as some 1 by C equivalent. I'm just labeling that as 1 by C equivalent. Let me write 1 by C equivalent is 1 by C1 plus 1 by C2. It's just a label, it's just an expression. But we'll see what this means. This will have some physical significance when we look at it in the short method. So my equation will become E minus Q3 by C equivalent minus I3R is 0. And of course I3 is dQ3 by dt. Now this equation here, this final equation, you should see that it is very similar to a single circuit. When you have a single capacitance, single resistance and a single battery. This equation. E minus Q by C minus IR is 0. That's what I have. E minus Q by C minus IR is 0. So the solution will be exactly the same as for a standard single capacitor, single resistance, single battery circuit, charging of a capacitor circuit. So I can directly write it as Q3 is equal to, the standard RC circuit has an expression of CE into 1 minus E raised to minus T by RC. It's just that instead of C here, I have C equivalent. I'll have C equivalent here and C equivalent here, where C equivalent is given by this expression. So you can just substitute that here and you will get the final expression for the charge as a function of time. So you can see we've spent a lot of time here and a lot of calculations to get to this point, but let's do this question by the short method and we'll see how cute that is. Let's do that on the next page. So you can probably already imagine what I'm going to do. I have EC1, EC2 and C3 and resistance. So I need the charge on Q3. I need the Q3 charge on C3. So I'm going to combine the upper two branches. So that will be, so what will be my E equivalent for this combination? E equivalent would be C1E plus C2E divided by C1 plus C2, that is simply E, and therefore my circuit will look like an EMF E. And what will be the C equivalent for C1 and C2? That will be C1 plus C2, then C3 and a resistance R. So now you can see that C1 plus C2 and C3 are in series. So I can just use the series formula for capacitance, and I can write 1 by C equivalent is 1 by C1 plus C2 plus 1 by C3, and therefore reducing my circuit further, E C equivalent and a resistance R. So I have reduced the entire circuit, which was looking a little complicated in the beginning, to a single capacitance, single resistance and a single battery, a standard RC circuit. And now you can see why I labeled this expression as C equivalent on the previous page during the standard method, because it is the equivalent capacitance when we combine these two capacitances in series. And now it's a very standard expression. You can just use the standard RC formula and you'll just get, I'm just going to write what we wrote on the previous slide as well. 1 minus e raised to minus t by R C equivalent. So of course you can see how quick this method was. Like I said in the beginning of this lecture, the short method is really useful in RC circuits. It displays its value in RC circuits, and now we're going to look at some RL circuits as well. But I hope you've understood this short method and its application here. Let's do a problem for you to practice and get comfortable. I'll go to the next page.